Hello and welcome to this video where today we're looking to see whether light is a particle or a wave. And so we're joining the debate when Newton and a guy called Huygen were arguing whether light was a particle or a wave. What we need to know is what Newton thought and what Huygen thought, and in particular how each of these explained reflection and refraction in terms of particles or waves. Newton's ideas were really widely accepted, and we need to have a look why. And eventually, in the end, it was determined that light was a wave, and we'll have a look at a brief bit of revision to look at why light, in the end, was thought to be a wave. So this is what Newton thought. Newton thought that light was a stream of particles. He called them corpuscles, so that's basically just an old word for kind of lumps of stuff. He explained reflection like this. So here you've got your corpuscle or your particle of light. It comes in, it hits a mirror, for example, and it bounces off. And he considered the normal and the parallel components of the velocity. And what he said was that basically both the momentum and the velocity that are perpendicular to the mirror change, and that when it hits the mirror, the velocity and the momentum become equal and opposite. So it's travelling in this direction with a certain velocity, and after it's hit the mirror, the perpendicular component of the velocity is the same size but in the opposite direction, but the parallel component stays exactly the same. And by doing so, he was able to show that the angle of incidence and the angle of reflection are equal to each other. So reflection was fairly straightforward. He had a slight issue with refraction though. So what he thought with refraction is he thought that your light particle came in, and then when it got to here, he explained that the light ray bent towards the normal because the particle got faster, but actually it didn't just get faster. Actually, the normal component to the boundary actually increased. So this component, as it enters, so as the particle comes along, suddenly there's an extra force acting on the particle from this particular medium, and so this velocity increases. But this velocity that's parallel to the boundary stays the same, and because of that, the resultant velocity bends towards the normal. So that's what Newton, so this basically sums that up, that's basically what Newton thought happened in terms of light and refraction. So reflection was fairly easy for him to explain, but refraction meant that he had to explain that light sped up as it went into an object like water or like glass. Huygen, on the other hand, came up with a different theory. He said, well, light's a wave. So he basically came up with the idea of wavefronts. So here we've got a source of light, and it gives out light in all sorts of different directions. So at some point later, the light ray that came from this source will have spread out and it'll form this wavefront here. His theory then said if you took any point on here, you could then consider further wavefronts as if this was a source of light and this was a source of light. So if you draw another wavefront here, you'd get this shape. Another wavefront from this source, you'd get this shape, and so on. And if you join all of these wavefronts up, you get this second wavefront. So he showed that basically the light was spread out, and you could tell where it was going to go. So when he looked at reflection, he considered light rays that were coming from a long way away. So instead of them being curved like this, he was just looking at a small portion of these, so the wavefronts were parallel. And as they came in, when they hit the mirror, basically he was able to look at the source of all of these light rays, and he showed that actually as this came in and then the light ray came out, that again the angle of incidence, the angle of reflection were equal to each other. So he showed exactly the same as Newton. When it came to refraction, however, what he was able to show is that as the light ray came in, once the wavefronts get into here, they actually get closer together, and he interpreted this as light slowing down, and as it does so, this part of the light ray slows down before this part, so it turns the light ray around and so it bends towards the normal. So he was also able to explain how light bent towards the normal, but he said exactly the opposite to Newton. He said that light slowed down as it passed from air into water and glass. So Huygens said it slowed down, Newton said it sped up. But scientists at the time, because Newton, sorry, there's a spelling mistake there. Because Newton was incredibly famous, and he got lots of things right about gravity and about calculus and maths and things. He was incredibly famous, so scientists were mostly inclined to agree with Newton and kind of ignore Huygen to a certain extent. So people at the time went, okay, Newton's definitely right, so therefore light is a particle. And it took a while for this then and people were incredibly convinced that light was a particle. And then along came Young, and he did an experiment where, and this is basically revision from last year's waves content. If you remember, he sent light through a double slit like this, and these two light rays basically, the light from here and the light from here diffract, and they overlap and they interfere. And so you end up with, if you have a screen, you end up with a bright part and then a dark part and a bright part, so you end up with the interference fringes on your screen. So the only way that you can interpret this is if light is a wave, because if light's a particle, what you would expect is the particles go through here and they hit on this screen and they hit on this screen, but nothing happens up here. So you'd end up with two bright parts and everything else would be dark. The only way you can get bright and then dark and then bright and then dark and bright and dark and so on is simply because light is a wave. So you have to go back and you really have to revise how you explain this. So for example, you get constructed interference here when the path difference is a whole integer numbers of wavelengths. And when that happens, you get constructive interference. In this case, you get destructive interference when the path difference is an integer plus a half lots of the wavelength. And if that happens, you get destructive interference when a peak and a trough meet, and so therefore you end up with destructive interference. And you can be asked any question about interference whatsoever in terms of double slits, and so you could be asked, for example, to calculate the fringe width, or you could calculate, for example, the distance between the slits, etc. So you really have to go back and you have to revise your double slit experiment in order to then answer some of the turning points questions. So in the end, scientists decided that light was definitely a wave, and that eventually they were able to measure the speed of light, and they eventually found that it did actually slow down when light entered into water or glass from air. So that showed that Huygen's theory seemed to be definitely right. So that meant light was definitely a wave. So in order to really look at things we need to know for the turning points exam, we need to know what Newton thought about light. We need to know that he thought it was a stream of particles or corpuscles and how he explained reflection and refraction. We also need to know basically what Huygen said about reflection and refraction and how they're different. We need to have a look at to see why Newton's ideas were more widely accepted than Huygen's, and virtually everybody agreed with Newton. And then you need to go back and revise how eventually light was determined that it was definitely a wave. So you need to go back and look at your interference experiments, particularly double slits. In the next video, we're going to have a very quick look at to see exactly how it was that the speed of light was first measured. But that was a video on waves and particles. So thank you very much for watching, and I'll see you again soon.